Hello, good morning everyone. Today we are going to continue our discussion related to Curse of Dimensionality, and we are going to focus upon the solution for the problem in general. In the last session, we had a discussion about the concept, and we have seen few approaches how to deal with this problem with respect to the nearest neighbor algorithms. But today, instead of restricting ourselves with the nearest neighbor algorithms, we are going to look at this concept in general, and we are going to propose the solution for this problem. So, let's once again look at this curse of dimensionality problem. So, what we mean by curse of dimensionality? If we go on adding the dimensions into our feature space, or if we try to increase the number of features those actually describe our instances in the feature space, then theoretically we may expect that increase in number of features is actually adding some more information into the problem domain, and we may expect that addition of number of features should increase the performance of our model or the ML algorithm. But it rarely happens. In fact, whenever we try to add the number of features, it rarely helps in improving the performance of our model. And the reason is, if we are having many number of features and if we are not having lots of training examples to train our model, then it results in overfitting, and this may decrease actually the performance of our model. So, in the last session, we have seen this example wherein we are assuming that the number of training examples is fixed throughout the experimentation. And what we have done is, we have performed the same experiment with the same number of training examples, but we have added the number of features. Those are describing our samples. So, what we can observe here is, as the dimensionality or the number of features increases, the classifier's performance increases until it reaches to the some optimal number of features. And after that, even though we go on increasing the dimensionality without increasing actually the number of training samples, this results in degradation of our classifier's performance. And this is what we say it is a curse of dimensionality. So, many number of features rarely help in improving the performance of our model. If we want to increase the number of features, then obviously we should increase the volume of data that is being used for training to maintain the similar level of performance, right? So this is not true that adding the number of features is adding the extent of information, right? But it will not necessarily add into the discriminative power of our classifier, right? So, I hope you must have understood this concept of curse of dimensionality. So, we are going to explain this concept today, and we are going to find out the possible solutions for this problem of curse of dimensionality. So, actually, the curse of dimensionality means the number of features that we have describing the instances is huge. So many features we are having. So obvious solution for curse of dimensionality problem is to reduce the number of features. So the possible solution is feature reduction, reducing the number of features. So to reduce the number of features, those we are using, we are having two kinds of methods or two types of algorithms. The first type of algorithms is known as feature selection algorithms, and secondly we are having the feature extraction methods. So we are going to focus upon these both kinds of algorithms. Those are being used to reduce the dimensionality of our feature set. So to reduce the dimensionality of our feature set or feature vector, we are having two kinds of algorithms. Those we are going to focus upon: feature selection algorithms and feature extraction algorithms. Right? Now, let us proceed to selection algorithms. So what we mean by feature selection? Let us assume that we have been provided with the initial set of features, and this feature set is described with n number of features. So we are having n number of features. Those are describing this feature vector f. So we are having this initial set of feature vector f that comprises of n number of features, x1, x2 up to xn. Now, in feature selection, what we are going to do is we are going to find out the subset of this original set f. We are going to find out the subset of this original set f. Let us denote this subset as f prime or f dash, right? So this f prime is the subset of f, and this includes the features x1 prime, x2 prime, so on up to xm prime, where this number of features m is less than the original number of features n, and this f dash or f prime, which is the subset of our original set f, optimizes certain criteria. So in feature selection, what we are going to do is we have been provided with the feature vector or the feature set f, which is the initial set that comprises of n number of features, and by using this feature selection method, we are going to pick the subset of this original set f, and this subset is denoted as f prime, wherein we are having the features denoted as x1 prime, x2 prime up to xm prime, and obviously m should be less than this n. So simply we are picking up few of the features from this original set, right? So if in original set I am having n number of features, I'll be picking up m features out of those n where m is less than n, and those features will form my subset f dash, and this f dash is actually optimizing certain criteria. So based on certain criteria, we are going to pick up few of the features. We are going to select few of the features from the original feature set, right? And we are going to form a new subset, and then this subset is being used for further implementation. So this is how we are reducing the dimensionality. Yes.
Hello, ma'am.
Yes.
Ma'am, could you explain again?
See, the solution for curse of dimensionality that we are proposing is reducing the number of features from our original feature set. So, feature reduction is the solution for curse of dimensionality. So, how to reduce the number of features? That is the question. And we are having here two solutions for this question. How to reduce the number of features. So, we are having feature selection algorithms and we are having feature extraction algorithms. We are going to look at both kinds of algorithms. So, let us see first what is feature selection algorithm. In feature selection algorithm, what we do is, given the initial set of features f that comprises of n number of features, we are going to find out the subset of this original set f such that in our subset we are having m number of features where m is less than n. So what actually we are going to do is, by making use of certain criteria, we are going to select few of the features from this original set f. So selecting the features from the original feature set f, we are coming up with a new subset f dash or f prime, wherein we are having m number of features and this m is less than n. So we are having a smaller subset of this f, right? And for further experimentation, we are making use of this subset of the features. So this is how, in this first solution, we are going to reduce the number of features. Those we are making use of for further implementations, right?
Yes, ma'am, but how we are
going to look at all those methods. I am just explaining right now the concept, what we mean by feature selection. So feature selection methods can be used actually to identify and remove the unneeded or irrelevant or redundant attributes from the data that actually do not contribute to the accuracy of the predictive model. Or sometimes these attributes or these features are in fact decreasing the accuracy of the model. So in feature selection, what we are going to do is, we are going to find out or identify the unneeded or irrelevant or the redundant attributes or features. Those are not actually contributing into the accuracy or performance of our model, right? So we are going to identify such attributes. Those are irrelevant or redundant, right? By making use of certain criteria, and by omitting such kinds of irrelevant features, we are going to pick the subset of the features out of original n features, and hence we are going to form this subset that we are going to make use of further, right? So this is what we mean by feature selection. So given a set of features, simply by applying certain criteria, we are going to select the features out of those original feature sets, right? That's all. So this is what we mean by feature selection. Now let us talk about feature extraction. So what is feature extraction method? In feature extraction, the original set of features is transformed, or the original set of features is projected into a new subspace which has smaller number of dimensions. What do we mean by that? See, in feature selection, what we did, based on certain criteria, we were selecting the features from the original set. But in feature extraction, obviously, we want to reduce the dimensionality of the feature vector, but instead of selecting the features, what we are going to do is, we are going to make use of original set of features, but using those features, we are going to project those features, or we are going to transform those features into entirely new subspace having the smaller number of dimensions. So projection to m dimensions, projection of original features to m dimensional, wherein m is less than n. So n total number of features in original set. So this is my original dimensionality. So what we are going to do is, these original feature sets are being transformed, or those are being projected into a new subspace having smaller dimensions. So m is less than n. So in fact, mathematically, if we look at this problem of feature extraction, what we are trying to do is, this is our original feature vector f that has been provided with n features. In feature extraction, by making use of these features, we are transforming, or we are generating new features in the new subspace. So in new set of features, so in new set we are having once again n features. So in this new set of features, we are not selecting the features as it is, but we are going to transform feature x into feature y. Right? So these features are being transformed. So some manipulation is being done on these original features, and the new features are being generated. These original features are being transformed to the new set of features y1, y2 up to ym. So there is some function f that manipulates on the original feature vector x1, x2 up to xn, and this function will produce the new feature vector y1, y2 up to ym with m dimensions. So once again, here m is less than n. So we are reducing the dimensionality. But here, instead of selecting the features as it is, we are going to transform, or we are going to project those features into entirely new subspace with smaller number of dimensions. That is what the difference in feature selection algorithms and feature extraction algorithms. I hope you must have understood the concept. If you are not able to understand, please let me know. We are going to focus upon feature extraction algorithm, most popular feature extraction algorithm, that is known as PCA, that is Principal Component Analysis. Right? So this PCA algorithm is being used to reduce the dimensionality of the feature vector. Right, by projecting the original feature vector into another feature space or another subspace. If you have any doubts, please let me know. Otherwise, we are going to look at the details of those algorithms. Yes. Have you understood what is feature selection and what is feature extraction?
Yes, sir. Yes, ma'am.
Fine.
Ma'am, actually, I want to know that PCA we are using. It is for just for means data preprocessing, or we are going to means it is like other algorithms like linear regression and all.
PCA is being used as one means for reducing the dimensionality. So PCA is being used to reduce the dimensionality of our feature vector. So you may say that it is kind of a pre-processing
Okay, ma'am.
to improve the performance of our algorithms.
Yes, ma'am.
Fine. So these feature selection and feature extraction algorithms are helpful, number one, for dimensionality reduction. Number two, these algorithms will improve or maintain the accuracy of our models, ML models. Third, it will simplify complexity of the model. And fourth, it will help us to reduce the overfitting. So feature selection and feature extraction algorithms are being popularly used prior to providing the feature vectors for training, right? So given the original training data set, first we may apply feature selection and feature extraction algorithms if required, and then these pre-processed training data sets are being used for creating the model, right? And the important aspects why actually these feature selection and feature extraction algorithms are to be used. Number one, these algorithms help in reducing the dimensionality of the feature vector. These algorithms will help improve or maintain the accuracy of the model. These algorithms actually simplify the complexity of the model because the dimensionality is reduced. And further, as the dimensionality is reduced, they reduce overfitting as well. Right? So these are the important aspects of these algorithms. So let's proceed with the feature selection algorithms in detail. So, as I stated earlier, feature selection algorithms are meant for selecting the subsets of the feature. So, if we have been provided with initial set of features, n number of features, say f equal to x1, x2 up to xn. So, the number of features those we have are n. Okay. Now, if we are having n number of features, possible number of subsets, those are equal to 2 to the power n. Are you getting me? If I am having n features, then how many subsets of this feature vector or this feature set are possible? If I am having n elements in the set, if I am having n elements in the set, then the possible number of subsets those I may have for this set are 2 to the power n. Do you agree with me? Yes?
Yes, ma'am.
Say for example, if I am having 4 features, f equal to, suppose 4 features I am having, 4 elements, 1, 2, 3, 4. So my n is equal to 4 here. So how many subsets are possible for this set with 4 elements? 2 to the power 4. That means we may have 16 subsets of this set F. Right? Which are those? I may have the single element sets. So 1, 2, 3, 4, single element. If we try to form the subsets with 2 elements, then what we may have? We may have 1, 2, then 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, right? And if we find the subsets with 3 elements, then we may have 1, 2, 3, 1, 3, 4, 2, 3, 4, 1, 2, 4, right? For 4 elements, obviously we are having 1, 2, 3, 4 and one empty set we may have, right? So overall, if I am having number of elements equal to 4 in my set, the number of subsets, possible subsets, those I may have is equal to 2 to the power 4, so 16, right? Now, if I am having those many subsets, and typically in real world problems, our value of n is comparatively high. So if I am having some high value of n, I may come up with huge number of subsets 2 to the power n, right? So practically it is not possible to enumerate all those sets and for every subset of features commons and come up with the greater subset of the features. So it is practically not feasible because we are having huge number of subsets 2 to the power n. So what is done is we are having some feature subset selection methods. We are having some feature subset selection methods. Those methods are optimum methods or the heuristic methods or the randomized methods. I'll repeat, the methods for feature subset selection might be the optimum methods or the heuristic methods or those can be randomized methods. We can use optimum methods if the hypothesis space or the feature subset space has a structure so that we can have some optimum algorithm that works in polynomial time. So if we are having such kind of a structured space or feature subspace, we may come up with such optimum algorithms. Otherwise, we may go with some heuristic based algorithms, some greedy algorithms, or even some randomized algorithms. So the important steps in feature selection algorithms are depicted in this figure. We are going to treat this feature selection method as the optimization problem, right? So feature selection is being treated as the optimization problem. So we are having some search algorithm. So in step number 1, what we are going to do is we are going to search the original space for possible feature subsets. So see here in this figure, we are having some training data. So we are having each example in this training data that is described with some set of features. So we are having here the complete feature set. In feature selection, what we are going to do is, this is the important part of our feature selection algorithm. So we are having 2 steps in feature selection. In first step, we will be having the search algorithm, right? And this search algorithm will try to find out the subsets of the possible features spaces, right? So this search algorithm will try to find out the feature subsets. In the second step, what we have is, we are having an objective function defined. So for whatever is the subset that is being selected by the search algorithm, that feature subset is being provided for this objective function. And this objective function will try to find out the score for this feature subset, right? And depending on the goodness of that score, depending on the goodness of the score of the feature subset, the algorithm further will decide which part of the search space need to be explored further, right? And this process is iterative. So once again, the new feature subset is being identified. Once again, the objective function is being computed for its score. Depending on that score, the goodness value is being computed. So how good that subset is, and based on that goodness value, if required, once again the remaining feature space is being explored. And this is how ultimately we are getting the final feature subset out of this process. And this final feature subset is being used for ML algorithm, right? So from this point onwards, our actual process starts. So this final feature subset is being created, and the training data now is being converted into this form after selecting the number of features from the original feature vectors. And then these feature vectors are being provided to train, right? So this is a simple scenario of feature selection algorithm. So these are two steps. Step number one is the search step, wherein we are finding out, or the search algorithm will try to find out the subset of the features. These subsets are being provided in the next step to the objective function, right? And our objective function will try to compute the score for this set of features. And depending on the goodness value of the selected subset, finally the optimal or near optimal subset with respect to this objective function is being selected, and this selected feature subset is provided for further implementation of our ML algorithm. So this is how feature selection works, right? Let me further elaborate this. So we have seen this feature selection algorithm. So as I stated, we are having the search strategies. Those are optimum, heuristic or randomized algorithms are being used for searching, and for evaluation strategies, we are having two kinds of algorithms: filter-based methods or wrapper-based methods. Filter methods are unsupervised methods, and wrapper methods are the supervised methods. So we are going to deal with these filter methods and wrapper methods in some details, right? But please remember, we are having the feature selection algorithm having two important steps, right? The search strategies are being listed out here: optimum search strategies, heuristic search strategies or randomized search strategies. And for evaluating those strategies, we are having the filter methods and the wrapper methods, right? And just I explained how it works. The objective function is being computed for the selected subsets and based on the score, right? The goodness value is being identified, and this is how we end up with the final feature subset out of this feature selection process, right? So in unsupervised methods or the filter methods, we look at the input only and we select the subset that has the most information, most relevant information. So we'll repeat, in filter methods, we look at the inputs and we select the subset that has the most relevant information. In supervised or wrapper-based methods, we train the model using the selected subset and we estimate the error on validation data set, and based on that, we repeat this process finally to come up with the exact subset of the features. So we are going to look at these two methods, filter method and wrapper method, with a diagrammatic representation like this. So see here, in filter methods, we are having training data with the complete feature set. We are having the search algorithms. We are having the objective function. Search algorithm will try to pick up the subsets of the features. The objective functions are evaluating those subsets, or rather objective functions are computing the score for these subsets. Based on that score, actual information contained in that feature vector is being found out, and if it is appropriate, then that feature subset will be identified as the final feature subset. If the information contained is not appropriate, then once again our search algorithm will try to explore the feature subspace further to identify a new feature subset. For this new feature subset, once again the objective function will be evaluated and then the information contained in that subset is found out. So this is the iterative process, and ultimately after completing this process, whenever I am getting my objective function with the proper goodness value, then that particular subset is being finalized and that is being used for further ML processing. In wrapper methods, what happens, please look at the difference in filter method and wrapper method. In wrapper method, what happens is, we are having the training data, no doubt. We are having the complete feature set. Then we are having the search algorithm, right? So this search algorithm is actually finding out the subset of the features. Now, see what happens here is, in wrapper method, this subset is directly presented to our machine learning algorithm or the pattern recognition algorithm, right? And for this feature set, this machine learning algorithm will prepare the model, and based on this model, the accuracy is predicted, right? And this process continues. So once again, the search algorithm will find out the new subset. For that subset, once again, our machine learning algorithm model is being prepared. The accuracy is being found out, right? Once again, the new feature subset is being computed and the process goes on repeating, right? So for whichever subset the ML algorithm is giving us the maximum accuracy, then that particular subset is being treated as final to prepare the final ML model, right? So information content is enough, right? We are going to look at some statistical methods.
Okay, ma'am. Ma'am,
to select these features.
yes, ma'am, yes,
Right?
ma'am. And ma'am, in wrapper method, we are using a machine learning algorithm for means feature extraction or feature selection, and again we are using the machine learning algorithm for training, like this.
Yeah, see, here what we are trying to do is, see, this step. In this step, actually we are trying to find out a good feature subset. So how to evaluate that feature subset, whether it is giving us result or not. For that reason, whatever is, say for example, if I am having initial feature vector with n features, right? And now we are finding out this feature subset, say f prime, with m number of features, right? Where this m is less than n. So we have selected few of the features out of n. So with these many features, m features, right? We are going to train our machine learning model, right? And we are going to find out the accuracy of the model with this m number of features. Right? Now, what next we are going to do? Suppose out of these n features, 1, 2, 3, 4 up to n features, in the first step, we have selected, say for example, first feature, third feature, eighth feature, 10th feature, and so on. Right? So for this set, for this subset, we are building the ML model and we are finding out the performance of that model in terms of accuracy. What next? In the second try, what we are going to do is, we are going to select some other feature subset. Maybe these features are there, but in addition, we may add some more features, or we may reduce some of the features from this set and we come up with another subset. So this is now a new subset of features. So to find out the performance of our ML algorithm with this new set of features, once again we are building the model, we are going to find out the accuracy, and we'll see whether this subset is doing good or whether this subset is doing good in terms of accuracy. Right? So this is how we are going to pick, we are going to select the features and we are finding out the performance of our algorithm using these features, and then we are going to finalize the final feature subset, which is giving us the maximum accuracy. And after finalizing this feature vector, then we are going to once again build our machine learning algorithm for final experimentation. Right? Because we have now found out which is the optimal subset of features.
Yes, ma'am. Here means we may use the same ML algorithm or different.
Same ML algorithm. Or
Okay.
it doesn't matter. So we have found out, see here, whatever is the feature subset that we have obtained, that is with respect to a particular machine learning algorithm. So obviously that particular feature subset should work properly for the selected machine learning algorithm. But if you want to try something else, then also you may try with the same feature subset and you may evaluate the performance once again. But typically these are the similar algorithms.
Ma'am, can you give an example for this means different
Yes,
algorithm
yes,
for this
yes,
yeah.
obviously. Yes, for example, say, once again, let us try to consider the simple algorithm, suppose k nearest neighbor algorithm. Right? In k nearest neighbor algorithm also, we are having this feature set with n number of features. Right? So huge feature vector we are having, and we would like to reduce the dimensionality. So obviously what we are going to do is, as I stated, we are going to select few features. right? So for these features, which algorithm I have selected? I have selected algorithm, ML algorithm as KNN algorithm, right? With some fixed value of K or some value of K, right? So suppose I am performing initially the experiments with K value. This K is the hyperparameter, right? So this K value equal to 5. So I have fixed this value of K equal to 5. I have found out this particular feature vector in the first pass. Then by making use of this feature vector, I'll use this KNN algorithm here and I'll try to predict the accuracy. Right? So here I'm making use of all training examples with the selected feature subset, and I'll be finding out the accuracy for my KNN algorithm. Suppose for this particular feature vector, my KNN algorithm has given me accuracy say 70%. Right? That is okay. What next I'll do? In the next iteration, my search algorithm will try to find out once again the new subset. Right? So let us assume that this is the new subset. So once again, out of n features, we have selected m number of features. So with these m features now, I am once again going to perform this k nearest neighbor algorithm for this entire training data I am having with those many features. And once again, I am going to predict the accuracy of my k nearest neighbor algorithm. So let us assume that now I have achieved the accuracy say 80%. So I am repeating this process number of times, and whichever is the accuracy that I find which is maximum or which is actually desired, then I will pick that particular feature vector. So ultimately, if 80% is fine, then I'll select this particular feature vector here at the end. And now with this particular feature vector, now what I'll do is once again I'll repeat this process, right, to form my final model of machine learning algorithm that I have selected. Right? So typically these machine learning algorithms are same because we have tested this particular algorithm with this particular feature vector. Right?
Ma'am,
Yes.
how will we decide that which method is good for our given problem?
Yes. That we are going to discuss next. See, we are having various statistical methods, right? Those will help us
Yes, ma'am.
to find out which features are contributing the most. Right? And based on that, actually we are going to select the features. So in fact, we are going to, I'll just show you one slide and then we'll conclude, and in the next session we are going to, with example, I'm going to describe how we are going to do that. So these are few of the statistical measures that we may have, right? So depending upon the input variable and the type of output variable, right, whether it is a numerical or whether it is categorical output variable, we are having various statistical methods, those we may use. So Pearson coefficient or Spearman's coefficient or ANOVA method, these are the various methods. So based on these methods, actually for every attribute or for every feature, it is possible for us to compute the content of the information, or it is possible for us to find out whether that input variable is relevant, whether that input variable is contributing in our output variable. And if yes, based on that score, if yes, we may pick that particular variable. Right? So this is really very interesting procedure. So in the next session, I'll be focusing upon that with example. Right?
Okay.
Okay.
Okay, ma'am. Thank you.
Fine. So I hope you have understood the basic concepts of filter selection and filter extraction methods. In the next session, we are going to dig into more and we'll see actually with example how, say for example, this Pearson correlation coefficient can be used to select the variables or to select the features, right? Fine. So let's conclude the session today. Thank you.